that I already have the first hypothesis of the squeeze theorem. I already have the function, the lower limit, the lower function, let's call it g of x, and the upper function. Since this is f, I'm going to call this one h. So I already have the number one hypothesis from the squeeze theorem, in which the function is sandwiched, we say, or squeezed between these two. All I have to determine now is the limit as x approaches 4 from 4x minus 9, and the limit as x approaches 4 from x squared minus 4x minus 7. If these two limits exist and they are the same, then I have my answer. If they don't exist or they're not the same, the squeeze theorem is not applicable. So what is the limit of the first function? Anyone?
7.
Very good. What is the limit from the other one?
Maybe 7.
So, is it? Let me see, maybe I copied it incorrectly. Then I conclude that the squeeze theorem is not applicable. And I cannot determine the answer.
How did you get 7 from the top?
It's positive here. You have to plug it in, right? As we always do, we always plug it in first, right? We always, for any limit, our first step must be plugging it in. That is always the first step every time we calculate a limit. And when you plug it in, since you get a number, you're done. It's not an indeterminate case. You cannot simplify. You don't have to simplify, rationalize, do anything. So,
do you plug in 0, or like how do you know what number to plug in?
So can anyone tell us which number we plug in? Anyone?
A, whatever your A is.
Of course. Yeah. Is that clear? Everyone?
Yes.
That's what we always do. So here we plugged in -4 in the first limit that we looked at. Then here we plugged in 0, right? That is the number. It's x approaches a. So that's what we calculate with. We are determining the limit as x approaches a, or 0. So that's what we have to plug in. So in this example, we are plugging in 4. 4 times 4 is 16, minus 9 is 7. 16 minus 16 plus 7 is also 7. And what do we conclude about this limit, whose function we don't even have? And when we calculated all the other limits in the previous sections, you calculated with plugging in numbers from approaching 4 from either side. So I hope that that is clear now. So what do we conclude about this limit of this function, that we don't even have an idea what it looks like?
The limit that the function must be 7.
Yes. By the squeeze theorem, it must be 7. And this is the first hypothesis, and this is the second hypothesis of the squeeze theorem. Okay.
I have another question.
Please.
When we're showing our work on homework and exams, do we need to explicitly say that? Like
Absolutely everything you see here, yes. On the written part of the exam that you have to submit, absolutely every line. Checking a graph or checking some number in with a calculator is not, it does not bring any credit.
I have a question as well.
Please.
Can a function be between two functions that approach a point and not even like go near that point or that limit?
But it is. It does.
Well, I'm saying, but can it be, could an f of x be between g of x and h of x, but not actually go near the point? Like maybe it just like turns around or something?
You may have a vertical asymptote there. But if it is squeezed between these two, and they do have the same limit, then no.
All of them.
But if they don't have the same limit, then the squeeze theorem is not applicable.
I get your question. I think it's like for squeeze theorem, it has to touch at that wherever A is. Those points are touching, so it's not like you could turn around.
But the functions don't have to be defined there.
So like if it was like a parabola, say f of x was like a parabola and it goes up and down, but the two functions approach and they go up and meet at a point, but the f of x technically in between the two, but doesn't even. Maybe I'm just not thinking about this right, but does that make sense?
But they have
So
to,
are you asking?
if the function is not squeezed between these two functions, and these two functions don't have the same limit, the limit does not exist, or it's not the same, then you cannot conclude this. I can look for another, or maybe a nicer graph.
Are you asking if g of x could be like 6 and h of x could be 7, and f of x could be in between those two?
No, like I understand that g of x and h of x, the two squeezing functions have to have the same limit, but I guess if a function is being squeezed, then it has to also have that limit if there's two squeezing functions. I mean, I guess that is the theorem.
Yes, that is.
Like function, like if a function can be squeezed but not have that limit, like if it before the
If you draw on a piece of paper like a graph of what you're trying to say,
like say okay, this is a horrible job. Yeah. So wouldn't these two functions be squeezing the inner function, but it wouldn't have the same limit?
So you're saying that the limits, but one has to be from below and the other one has to be from above. What you graph, they're both from above. So you're not squeezing the inner function. In your graph, the inner function is not squeezed between the two functions.
Sorry, yeah, that makes sense.
Yeah, is that clear?
Yeah. So
That's okay. I mean, we have to discuss these things. Whatever you...
What if you just like turned it sideways and it was squeezing from the
If you
top?
turn it sideways, it may not even be a function by the vertical line test.
so those two that you have going to positive infinity, those two lines, the parabola just goes under the two. It would have to go up to positive infinity as well.
Yeah. Okay.
Is that better?
Part of the squeeze theorem.
Like you said, it wouldn't pass the vertical line test.
I love these discussions, so this is very important to me, that you are discussing and you are answering your own questions, actually. Great job. Okay, that's all I had to say about 2.3, and I'd like to move on with 2.4. The precise definition of the limit. This is the only proof in this class. It's an important proof. We're only going to look at linear functions, only the simplest possible function to work with, but it will take me a few minutes to explain what this is all about. So when we talk about the precise definition of the limit, in short, we like to say the epsilon delta definition. And when we say that, we know what we mean. We mean the precise definition of the limit, the epsilon delta definition. A student some time ago asked me, what about this? What is this? I know that delta is this. True. This is the uppercase delta and this is the lowercase delta. They're Greek letters. Okay, so what is this all about? So first of all, let's take a look at the following scenario, discuss it, write the definition, the epsilon delta definition, And then look at examples. So I'm going to just draw a function. Here is a function, f of x. I'm going to pick a and L. And I would like you to let me know whether this is acceptable. The limit of f of x as x approaches a is L. Would you agree with this?
Yes.
According to the graph, it doesn't matter whether it's defined or not, but according to the graph, this is obviously correct. And now I'm going to put in words what this represents. We will take an interval, tiny interval, around the limit. It is a symmetric interval, meaning this length is the same with this length. This point here is L plus epsilon. This point here obviously would be
minus epsilon.
L minus epsilon. So obviously the width of this between L and this point, of course, it's epsilon. So let's put this in writing. For every epsilon positive, has to be a positive number. For every epsilon positive number, there exists, or if you prefer, I will find, for every epsilon positive, there exists, or I will find a corresponding, of course, delta greater than 0. Stop for a moment. Let's go back to the graph. What am I really saying to you? I'm saying this. I draw a horizontal line. I draw a horizontal line. These horizontal lines meet the graph in two different points. From those points, I drop vertically to the x-axis, and I see that there exists now an interval around A. So for every epsilon positive, I will be able to find a corresponding delta. We don't know which delta that is for a moment. So I construct the graph by drawing horizontal lines. They meet the graph, and then I determine the corresponding x values for those two. Now the question is, this could be delta between A and the rightmost point, or this could be delta, not both, of course. So I'm going to call this delta 1 and this delta 2. Obviously they are not equal. So I debate now with myself, which one do I pick? Let's go back to the definition and then we'll come back to the graph. Okay, so for every epsilon positive, there exists, or I will find, a corresponding delta positive, such that, and this will give us which one to pick, delta 1 or delta 2, such that anytime I pick x close to A, but this is very important, how close. I'll put in parentheses, distance between x and A is less than delta. One more time. We have to repeat this several times till it's clear and we can explain what happens again. So for every epsilon near L, of course, I will be able to find a corresponding delta near A. Which one you will tell me in a minute. So according to the graph, I determine this one, which is definitely smaller than this one. So for every epsilon there exists, or I will find a corresponding delta positives, such that anytime I pick x close to A, so that the distance between x and A is smaller than delta, watch me pick. Watch me pick. So because this is smaller, the interval around A has also to be a symmetric interval. So if I choose delta 1, then I will have this interval. This will be my delta 1, and this will be my delta 1. And now watch me choose. And every time I pick x close to A, distance between x and A is less than delta, f of that x will fall in the vicinity, or near in the vicinity of L. In other words, close to L and the distance. We're not going to write this. I'm trying to explain it. Well, you're going to see it's going to be one line. Close to L and the distance between L and f of x is less than epsilon. So watch me pick x. So if I pick x here, look what happens. Will f of this x, if I pick this x, will f of this x fall within between L and L plus epsilon? Will it fall so that the distance between L and itself is less than epsilon?
Yes.
If I pick x here, let's see. Will f of x, of this x, will fall within the distance of within epsilon between L, between that value of f of x and L, will it be smaller than epsilon?
Yes.
Now, if I use the big delta, the delta 2, then this will have this symmetry, right? I have to use a symmetric interval around A. Watch me now picking another x. Ready? So then you know exactly which of the two deltas I need to pick. I have to pick the small delta, the delta 1, or the big delta, the delta 2. Did you see what happened? When I picked delta 2 and I picked x here, was f of x for this point, for this x value, was that f of x within epsilon away from the limit or not? No, it was outside of the interval. Which means that I need to pick which of the two deltas. Always pick the which word I'm missing there?
Smaller.
Smaller, maybe?
Very good, awesome. Always. Because it would not work. If I pick the big one, the definition fails. Okay, we don't write all that, so I'm going to show you some mathematical symbols. This symbol for every. This symbol, there exists. This symbol, such that. Distance between x and a is denoted by the absolute value of x minus a. Distance between f of x and L, can anyone tell us how to write that? If the distance between x and a is this, what will be the distance between f of x and L? Very good. Indeed, the absolute